So let's begin. So having finished properties of matter in the last lecture, we will start with the next section of physics, which is simple harmonic motion. So to begin with a few basics, basic definitions. Periodic motion. Any type of motion which is repetitive and repeats with a definite cycle or repeats with a definite time period is called a periodic motion. So any repetitive system or motion which repeats in identical cycles with a definite time period is called a periodic motion. For example, you have the oscillation of a pendulum. Rotation of the earth about its own axis. Then you have any type of orbital motion. Or you have the case of a ball bouncing elastically. These are all examples of periodic motion. Now further within this, we have a special category of periodic motion, which is called an oscillation. So we've included an example of oscillation, that of the pendulum, within the category of periodic motion, but we'll see that oscillation is actually like a subset of periodic motion. It's a specific type of periodic motion. So an oscillation is a to and fro motion with definite amplitude and time period. With respect to a mean position. So mean position is in fact the stable equilibrium position. So that is the subcategory of oscillation, which is obviously a periodic motion. So it is a type of periodic motion. So many examples of oscillations. Okay, now we'll see next that simple harmonic motion is a further subcategory or special case of this oscillation. Okay, the specific type of periodic motion which is to and fro with respect to a mean position or stable equilibrium point. Okay, so next up, let's understand the special case of simple harmonic motion. But before that, what about any system that oscillates? For any system to be able to oscillate, okay, it must have a stable equilibrium position. That is local minima of its potential energy. And the net force must be conservative and restorative with respect to the equilibrium position. So these are the two necessary conditions, necessary and sufficient conditions for a system to have the property of being able to oscillate. So we will understand more about this when we look at physical examples of oscillations and particularly simple harmonic motions. So make a note of this definition, then we'll discuss, or rather make a note of this point. Next, we'll come to the definition of simple harmonic motion. Okay, now about simple harmonic motion. This is a very specific case of an oscillation. So it is a case of an oscillation along a straight line, first of all. Okay. So technically pendulums cannot be simple harmonic motion because they are angular motion. The path is circular or angular. Simple harmonic motions are only oscillations that happen along a straight line or along an axis. Okay. And further, an oscillation along a straight line such that the displacement from the mean position, that is what we call a harmonic. That is where the term harmonic in SHM comes from. Harmonic means sinusoidal or sine function. So it is a harmonic function of time. So basically what it means is that suppose x axis is the axis of motion. Okay. X equal to 0 is the mean position, suppose. Then x should be a sine function of time. Okay, so when we look at the x versus time graph, it should look like a sine function. That is the basic definition of the term simple harmonic motion. In fact, the two terms simple and harmonic come from that. Simple comes because it's a one-dimensional motion or straight line motion. So that's the simplest possible thing. So this should be, it should be a sine curve. It should be exactly like in shape. It should be just like the curve y equal to sine x that you are used to. Be that same shape of curve. So x versus t should be a sine curve or a sinusoidal function or a harmonic function. So here the term harmonic actually means the same thing as the sine function. Okay, so once we understand this, we come to the next thing, which is the general equation of simple harmonic motion. Given by the relation x is equal to a sine of omega t plus phi, okay, where this is the Greek symbol omega and this is symbol phi. Okay. So here x is the displacement from the mean position, which is x equal to 0, as a function of time t. A, omega and phi, all three are constants such that the dimension of A is length, the dimension of omega is inverse of time, and the dimension of phi is 1, or it is dimensionless. So amplitude is usually in A is usually in centimeters or meters or even millimeters, whatever. Omega is typically in radians per second, and phi is in SI unit expressed in radians. Okay, so make a note of this first, then we'll understand each of these terms. Okay, so now let's look at the definition of some of these terms. So the first thing we'll see here is the amplitude capital A. So you know that basically sine theta is between -1 and 1 for all real values of theta. So therefore, this term sine of omega t plus phi will also be that same range for all values of time t. So therefore, x ranges between -a and +a, or mod x is always less than equal to p. So that is why the quantity A is called the amplitude. Equal to the maximum displacement from the mean position. Right? So that is the definition of the quantity capital A in the general equation of SHM, which you have seen above. In this general equation. Okay, next we'll understand the quantity called angular frequency omega. So to understand the relationship of the angular frequency omega with the frequency of oscillations, that is the number of cycles per second, or to understand its relationship with time period, the time taken for one full cycle, you have to understand the nature of this graph. You can see here that it varies between plus a and minus a. Now this is one cyclical time, or what we call the time period. So the same thing as this. So since we know that in general, sine of theta is the same thing as sine of 2n pi plus theta, where n is etc. Okay. So therefore, sine of omega t plus theta plus phi will be the same as sine of omega into t plus n times capital T plus phi. This one here is theta actually on top. So comparing this equation from the above equation, you can see that omega into n times t should be equal to 2n pi, or omega t should be equal to 2 pi, where t is the minimum time, or what we call time period, for completion of a cycle of oscillation. Okay. So we have the relation that time period is equal to 2 pi by omega, or frequency is omega by 2 pi. And that is why omega is called angular frequency. Because frequency equal to omega by 2 pi means omega is equal to 2 pi. So it is called the angular frequency. Okay. Frequency is measured in hertz, where 1 hertz is 1 cycle per second. So for example, if the time period of some oscillation is 20 milliseconds, then the frequency will become 1000 by 20 or 50 hertz.
Sir, I didn't understand the comparing part.
If you see, if you look at a standard sine graph, no, what is the cycle in which it repeats itself? That is the circular nature of sine function. No? Every 2 pi it repeats itself. You understanding now? Sine of theta always repeats itself as sine of 2 pi plus theta. For every 360 degrees it repeats itself. So if we generalize this, this becomes sine of 2n pi plus theta. Okay, is this statement clear first?
Yes, sir.
Okay. So now see, we are talking about SHM. So x is a sine function of time. Okay. So when the motion repeats itself, I should replace the time with t plus capital T, or after the second cycle 2t, and like that after the nth cycle, it should be nt like this. Okay. So it should come back to the same thing when time is replaced with this now.
Yes, sir.
Okay, so sine of omega t plus phi should become equal to sine of, now replace t with small t plus capital T after the first cycle, or just continue this for n cycles and it should become omega of t plus nt plus phi. Okay. Compare this thing, it should be comparable with this. And if you compare this side, it should be comparable with this.
Yes, sir.
So think of omega t plus phi as a theta. So now this whole thing, omega t plus omega into nt plus phi. So this term is actually omega t plus phi ko alag le lo plus n times omega capital T. So this is my theta and this is now my 2n pi. Got it now?
Yes, sir.
Okay. So that is why now comparing the two, we can say that n times omega t is equal to 2n pi, or omega is equal to 2 pi upon time period. Or invert this and time period is 2 pi by omega. So frequency is omega by 2 pi, because frequency is inverse of time period. Okay, so hope this is clear, beta.
Yes, sir.
Understood now? Oh. Now the next thing is the last of the three constants in that equation. So it is called the phase constant or initial phase.
So could you please scroll back up? I wasn't finished writing.
Okay, and scroll back. Okay, this part or earlier?
The earlier parts.
Okay. Yeah, the definition of angular frequency. Yes, finish.
Done, sir.
Right. So now this comparison thing also, I hope all of you understood how we are able to just. So it is basically the property of sine function. In fact, later now what we'll do is when we are looking at simple harmonic motion in more detail, we'll relate it with the projection of uniform circular motion. So just like in uniform circular motion, every time period you complete one cycle. So the angular displacement completes um, one cycle of 2 pi. Every time your angular displacement has completed one full circle, it is increased by a factor of 2 pi. Okay, so that's why this function repeats itself every 2 pi. Both the sine and cos functions, they repeat itself every 2 pi. So the amount of time equivalent to it repeating the cycle by 2 pi is such that omega into capital T, because that is when I increase the value of time from small t to small t plus capital T, it should complete one cycle. So that means the quantity inside the bracket for sine, this whole thing, it should increase by a factor of 2 pi because one whole cycle is completed. So how much it is increased by omega into capital T. So that should be equivalent to 2 pi. So that's how we get this relation that omega capital T is equal to 2 pi. So that's the relationship. Okay. Now we come to the third thing, the phase constant or initial phase. That is the name given to this other constant. In the equation, x is equal to a sine omega t plus phi. So remember, this was a dimensionless constant. Phi is a dimensionless constant, which is measured in radians in the SI system. So what phi determines is that the value of phi determines the initial position of the from where the SHM is starting with respect to the mean position. So it actually determines initial position and velocity. So we'll discuss about velocity also in a bit, but here we'll just talk about initial position. So if x is this, so from this we can see that at t equal to 0, that is initially, the value of x we'll write as x naught, and that is how much? It is a sine phi. So that is the significance of this phi. It determines where the motion is started from. Okay, so for example, if phi is equal to 0, that means x naught is 0. So that means the motion, or in this case, the SHM, starts from the mean position. That is x equal to 0. So the graph of x versus t will look like that. It will reflect that fact that the motion has been initiated in such a way that it started from the mean position. And what it's doing is that in the first quarter cycle, it is going to the positive amplitude plus a. Then in another quarter cycle, half a cycle of the whole motion is over. So it's back to the mean position. But in 3/4 cycle, that is another quarter cycle later, it has gone to the negative extreme. And finally, this is a completion of one cycle. But that is the case when phi is 0. Now we can see a contrasting situation. If the phase constant is pi by 2 for another SHM, then x naught becomes plus a. And you can see that x in general becomes a sine omega t plus pi by 2, which is equivalent to saying that x is equal to a cos omega t. So the sine omega t and cos omega t graph are basically the same shape, but they have a phase difference of pi by 2. So now for this SHM, the motion will look like this. It started from the positive extreme. First quarter cycle is back to mean position, then minus a, then back to mean position, then back to the initial position from where it started, and then the cycle repeats itself. So this is going to be this one where our phase constant is plus pi by 2. So the starting point is the positive extreme instead of being the mean position. This is completion of one cycle. This is half a cycle. This is quarter of a cycle. This is 3/4 of a cycle. So this placement of this graph, where it is starting from at t equal to 0 and which direction it is moving in, that is determined by the phase constant phi. So I've given you two easy examples of the phase constant, two most basic ones, 0 and pi by 2. We will see more general examples also as we go about, but first of all, write down the definition and the significance of phi, which is the phase constant. Okay, so let's look at some more examples. So an SHM given by the equation x is equal to where, let's say, x is in centimeters, t is in seconds. So find amplitude, time period, frequency. Second, find the position x and velocity v of the particle in SHM at t equal to 0 and then again at t equal to 1 second. Just try this question out, people. Yes, very good, Varun. Your answers are correct for the first part. So amplitude you can directly see is 12 centimeters. Omega we can see is pi by 3 radians per second. So now since omega is 2 pi upon time period, so you can see the time period is 6 seconds, right? And frequency therefore is 1 by 6 hertz. So frequency can always be a fraction because it means that basically 6 oscillations are completed in 1 second. So in one oscillation, 1 second only 1/6 of an oscillation, or whatever 0.167 oscillations are completed or cycles are completed. Yes, that's correct. So these are the answers for the first part. Yes, correct for second part also, Varun. Very good. Now you have to just tell the velocity. Now just a hint to you how we calculate the velocity of anything that is moving along the x-axis. V is dx by dt. So just use that definition, okay? Okay, so let's look at this. So x is equal to 12 sine pi by 3t plus 5. Or in general, what we can say is x is A sine omega t plus phi. So V, which is dx by dt, will become 12 understand this as a general equation. You can see that when you differentiate this, okay. So V is 4 pi cos pi by 3 t plus pi by 6 in general. Okay. So this is velocity as a function of time. This is position as a function of time. Now we'll use both of these. Okay. So in the A part, at t equal to 0, the initial position we can write as x naught. It is 12 sine pi by 6. So that is plus 6 centimeters. And the initial velocity, now here the velocity is in centimeters per second, because this omega term, this is in radians per second, and this amplitude is in centimeters. So A omega is in centimeters per second. Okay. So velocity is 4 pi cos pi by 6, and cos pi by 6 is root 3 by 2. So 2 root 3 pi centimeters per second. So this is the velocity and position at t equal to 0. Yes, very good, Varun, that's correct. At t equal to 0 seconds, it's 2 root 3 pi. Whereas the second one, answer will be 0 for velocity. At t equal to 1 second, you can see x will become 12 sine pi by 3 plus pi by 6. That is 12 sine pi by 2. So it's plus 12. It's at the positive extreme. Whereas v will become, sorry, 4 pi, but into cos of pi by 2. So that will be 0. Which makes sense, because when the particle is at the extreme position, its velocity is always 0 in an SHM. So this type of question is basically called kinematics of SHM, that is the equations of motion of SHM. Okay, so hope this part is clear. Now we move on to the next part, velocity and acceleration. You've already seen through that question how to calculate velocity in SHM. So given x is equal to a sine omega t plus 5, and acceleration is dv by dt. So acceleration comes by differentiating this term above, a omega cos omega t plus 5. So when you differentiate this term, a omega is a constant. Differentiation of cos is minus sine. And because you're having to use the chain rule, and the omega inside also comes out. So the acceleration becomes minus a omega square sine omega t plus 5. So velocity is this, you see. So this is the relation for acceleration and velocity. Now we can see that in the equation, see that velocity also varies periodically. In fact, that's also a sinusoidal relation. With the time period of 2 pi by omega, or frequency of omega by 2 pi, and with what we call the velocity amplitude, that is the maximum magnitude of velocity, equal to a omega. So this becomes an important term here. So just make a note up to this point, then we'll discuss more about the relationship between velocity and acceleration and all these things. Yes. Now, before we come to the relation of acceleration, one more thing we'll see here, that and V, which is A omega cos omega t can phi, can also be written as A omega sine of omega t plus phi plus pi by 2. Okay, because you know the general trigonometric relation that sine of theta plus pi by 2 is cos theta. So what this tells us is that V has pi by 2 phase difference with respect to this thing, x. So for example, if we compare a graph of x equal to a sine omega t, and that same thing if we look at the velocity, it is a omega cos omega t. So we'll see that the velocity in the graph will be like this. So there's that pi by 2 phase difference. So this means that at x equal to 0, that is mean position, v is equal to plus minus a omega, that is maximum speed. And at x equal to plus or minus a, that is extreme position, v is equal to 0.
So can you please explain the red colored part when x equals to 0?
Okay, people, so this is clear, I hope. Okay, now moving on to acceleration. So that phase difference concept should be clear. Now moving on to acceleration, we have acceleration is equal to minus a omega square sine omega t plus 5. So again, the same thing, we see that acceleration also varies periodically in the same way, and it's harmonic or sinusoidal with respect to time, with same time period 2 pi by omega, same frequency omega by 2 pi. Okay. Then maximum magnitude of acceleration is equal to how much? Capital A omega square. So this becomes another important formula. Okay. And acceleration has phase difference of pi with respect to displacement. Okay, because sine of omega t plus 5 plus pi is equal to minus sine of omega t plus 5 because of this. So what this means is that at x equal to 0, acceleration is also 0. Mean, or what we therefore also call the equilibrium position. Equilibrium means that acceleration is 0, net force is 0. Okay. But at x equal to plus a, the acceleration is minus a omega square. At x equal to minus a, acceleration is equal to plus a omega square. So at extreme position, magnitude of acceleration is maximum and direction is towards mean position, that is towards x equal to 0.
Sir,
Yes.
so where do we have to substitute x equals to a to get the value of acceleration?
No. So the point is, see, na, ki there is a phase difference of pi na, between this and this. So you're understanding my point. So x is a sine omega t plus phi. So at this point of time, what is the acceleration? It is minus a omega square sine omega t plus phi. Na? You can see the relationship between the two. Na? There's a phase difference of pi. So at a time when x will be plus a, what is the value of this sine term? It is plus 1. Na? So what will be the value of the acceleration term? It will be minus a omega square. Understood the point? यहाँ से जब x का value plus a है, what that means? At that instant, sine omega t plus phi is how much? It is plus 1. Na? So correspondingly, how much will be the acceleration at that time? It will be minus a omega square.
Got it.
Similarly, got it? So it's like that.
Thank you.
So they have that kind of relationship that when you are at the positive extreme, then you have maximum negative acceleration, and when you are at the negative extreme, you have maximum positive acceleration. Okay, so finish with this now.
Yes.
Okay. Okay. Now one more important thing over here is the relationship between acceleration and displacement. From the above equations, you'll see since x is when x is described like this, then the acceleration, which is basically d2x by dt square, that becomes minus a omega square sine omega t plus phi. So comparing these two equations, you can see that acceleration, or you can also write it as d2x by dt square, is minus omega square times x. So this is the most important thing over here. This is the condition for SHM. That is, the acceleration's magnitude is proportional to the displacement's magnitude, and acceleration's direction is opposite to displacement. Or if it is opposite to displacement, that means it's always pointing towards the mean position. So acceleration always points to the mean position. That is x equal to 0. So if you visualize a particle that is doing SHM along this line here, between x equal to plus a and x equal to minus a, anytime the particle is at a position like this, its velocity can be like this or its velocity can be like this, but its acceleration will definitely be like this. So its x is positive, so its acceleration is negative. Okay. Whereas when it's at a position like this, again its velocity could be either coming towards the mean position or going away from the mean position, but its acceleration will be pointing towards the mean position. So at this position, x is negative and acceleration is positive. So wherever it is, so when it reaches the extreme position, for example, here its velocity becomes 0 for a moment, but the acceleration is maximum. It is a omega square along the negative direction. When it's here, again, velocity is 0 at that instant, but it has maximum acceleration in the positive direction. At the mean position, the acceleration is 0. So this is what this tells us, that acceleration's magnitude is directly proportional to the displacement from mean position, and the direction is always opposite to x. So this is the condition on the acceleration for SHM. Whenever we have a system which possesses this condition, this property, that is acceleration is proportional to displacement in magnitude and opposite in direction, it means that it will perform SHM.
Here the graph of acceleration will be same as the graph of displacement.
Yes. No, it will be same in the sense that it will have the opposite phase. No?
Yeah, it will start from down first, right? Minus A.
So for example, if your position is x is a sine omega t, then position versus time is like looking like your regular sine graph, but the corresponding acceleration will become minus of this. No, so the acceleration will be minus of a omega square sine omega t. So that one will look like this now. So at the mean position, both are zero, but otherwise they are opposite. So there's a phase difference of pi. Okay, so hope this is also clear, people. Okay, so this brings us to the final point. From the condition of acceleration, we understand what is called the dynamical condition for SHM. So the word dynamics is to do with force. Okay, so you'll understand that what is the condition on force so that a system will perform SHM. So since acceleration or d2x by dt square is equal to minus omega square x, so therefore for a particle of mass m to perform SHM along x-axis with equation like this. So for this to happen, the net force acting on it should be equal to mass into acceleration, where F now I'm referring to is the net force on the particle. I'm writing it in 1D because it's motion along the x-axis. So the net force should be equal to minus m omega square x, or what we write as minus kx, just like a spring force. So the magnitude of the force should be proportional to displacement, and the direction should be opposite the displacement or pointing towards mean position, where the quantity k is equal to omega square m. It is called the force constant. So in the technical language of SHM, we say that this is a restorative force because it always points towards the mean position. It's a restorative force which is proportional to displacement. This term F is equal to minus kx. You think of it like this. Restorative means it's always pointing towards the mean position. So it's a restorative force proportionate to displacement. So the term restorative here itself means that it points to the mean position. So this is a condition for SHM, that the net force or F is a restorative force that is proportional to displacement. This is the dynamical condition for simple harmonic motion. Okay, people, so hope this is clear. So with this, we complete the first section of SHM, which is about the kinematics of SHM, the relation between displacement and time, velocity, acceleration, all these things. And we've sort of taken an introduction into the second part, which is the dynamical part, or where we solve the dynamics of SHM. That is, from the forces acting on a particle, we can determine how it's performing SHM with the correct condition that the net force should be like this. It should be restorative and proportional to displacement. So we will look at spring mass systems and their SHM through this kind of situation in the next lecture. And with that, we'll conclude SHM and we'll come to the next part of oscillations, which will be the pendulums, which do what is called the angular harmonic motion. This is the simple harmonic motion, which is harmonic motion along a straight line, and angular harmonic motion is angular motion instead of straight line motion, but which is harmonic with respect to time or sinusoidal with respect to time. So simple pendulum, physical pendulum, all those will be examples of that. So hope all this is clear. I'll send you the notes and recordings soon. That's it for today's session. Wish you all the best. Thanks for attending.
All right, so thank you, sir.